Welcome to homework.
Okay, we've got light whose wavelength is 278 nanometers. That is lambda equals 278 times 10 to the negative ninth meters, right? That's a nanometer. And the question is, what is the frequency of this light? Well, you can always relate frequency of light to wavelength through the following equation, and that is that the speed of light, right, is going to be equal to the wavelength of the light times the frequency of the light. C equals lambda nu. Now, the reason for this is that uh, C is in meters per second, right? And we know that lambda can be written in terms of meters. And that frequency is always per second, right? How many times per second? So seconds inverse, which is the same as saying, meters per second equals meters per second, right? Seconds inverse equals 1 over seconds. Okay, so if we've got a wavelength and we want to know the frequency, let's go back to this equation, C equals lambda nu. And what we need to do is solve for frequency, right? So we just we divide both sides of this equation by lambda, do a little bit of algebra. C over lambda equals frequency, right? So speed of light divided by 278 times 10 to the negative 9, where the speed of light is 2.9998 times 10 to the 8 meters per second. We can divide this by 278 times 10 to the negative ninth meters. All right, so our final answer will be per second after the meters cancel. Let me type this into my calculator. 2.9998 E8 divided by 278 E-9. E I'm using in place of 10 to the whatever. That's a calculator shortcut. Point is, when I am done, I get out 1.079 times 10 to the 15th seconds inverse. That is the frequency. Okay, now we want to know the energy of a mole of photons with that same wavelength, right? Well, E energy equals H nu. Right? That's the relevant equation. The energy of light is equal to Planck's constant times the frequency of that light. Okay, so we know the frequency of that light now. We just discovered it. So this should not be too bad. The other thing is that we have, as this is written, this would be for a single photon, right? But if we want to know what that would be for a mole of photons, we simply need to multiply it by Avogadro's number, right? One photon times Avogadro's number is a mole of photons. So we'll put this Na there to be Avogadro's number. And let's get to work. Planck's constant, 6.626 times 10 to the negative 34. That's joules times seconds. And we just discovered that the frequency of light is 1.079 times 10 to the 15th seconds inverse. And Avogadro's number does not have units, it's just a number, right? So 6.022 times 10 to the 23rd. All right, and let's put this all together into my calculator. 6.626 e negative 34 times 0.079 e15 times 6.022 e23 I get 430540. And if we wanted, we could put this in terms of kilojoules. Right, this is joules. So, we've got a couple options. We could say this is 4.31 times 10 to the fifth joules, or we could say that this is 431 kilojoules. That's rounding to 3 sig figs. And that's how many sig figs we had. Okay, what region of the electromagnetic spectrum is covered by the spectrum again? Well, I cannot see the spectrum. You have not posted the picture of the spectrum, so there's no... wait, but you know what? I can Google the spectrum of aspirin. Let's do that. UV is aspirin. Okay. And what I see is that it looks a bit like this. Okay. And this, maybe say 400 here, and then nothing all the way out to 800. How about that? Great. Okay, so what color is that? What color of light corresponds to 238 to 278 nanometers? Well, it's basically in the like if we look at UV Viz light spectrum, how can I put this? This is where violet starts, right? And red is all the way out here, and this is all UV, ultraviolet, right? So aspirin absorbs in the ultraviolet region. Okay? So it doesn't really absorb in the color region, which means that all colors will be represented if you were to view a solution of aspirin or view aspirin. So we expect that aspirin should be white or colorless, right? Because it doesn't absorb any light in the visible region.